Hello to all my viewers. This is Dr. Dhaval Maheta, and today we'll understand auto-regressive integrated moving average, that is ARIMA models in R. Box and Jenkins first introduced ARIMA models. The term deriving from AR is autoregressive, I is integrated, MA is moving average. So we'll understand ARIMA models with a small example. In the first column, we are having the day. In the second column, the temperature. So on the first day, the temperature is 75, second, 78, third, 80, fourth, 77, fifth, 82, and on the sixth day, the temperature is 79. We want to predict the seventh or eighth day temperature based on some models. So the first model is auto-regressive model. This is a AR model. Imagine you are trying to predict tomorrow's temperature based on past few days. In an AR model, you will assume that the tomorrow's temperature depends on the temperature of the previous days. For instance, if the last few days have been warm, tomorrow it's likely to be warm too. The model uses the weighted average of the past observations to make the predictions. In an AR1 model, order 1, tomorrow's temperature is the weighted sum of today's temperature. So tomorrow's temperature is equal to phi into today's temperature plus the error term, which is denoted by epsilon. So here phi is the coefficient and epsilon is the error term. Let's understand the AR model on the same example. How we will calculate tomorrow's temperature? So it will be C, which is a constant mean temperature, C plus phi into 75 plus the error term epsilon 1. On the second day, C plus phi into 78 plus epsilon 2. On third, C plus phi into 80 plus epsilon 3. Fourth, C plus phi into 77 plus epsilon 4. Fifth, C plus phi into 82 plus epsilon 5. Sixth, C plus phi into 79 plus epsilon 6. So this is how AR model works. Generalized ARP model. A generalization of the AR1 model is the ARP model. The number in the parenthesis denotes the order of the auto-regressive process and therefore the number of lag-dependent variables that the model will have. For example, the AR2 model will be an auto-regressive model of order 2 and will have the form yt is equal to phi1 yt minus 1 plus phi2 yt minus 2 plus ut. Similarly, the ARP model will be an auto-regressive model of order p and will have p lag terms as in the following. The last term is p. Moving average models. Now let's say you are predicting tomorrow's stock price. In an MA model, you will assume that the tomorrow's price depends on the combination of past forecast errors, the differences between the predicted and actual values. So if the model consistently underestimates the stock price, it would adjust the future predictions upward to correct for this. In an MA1 model, order 1, tomorrow's temperature depends on the forecast error from today. So tomorrow's temperature is equal to theta multiplied by today's forecast error plus the epsilon. So here theta is the moving average coefficient and epsilon is the error term. Same example we will understand with the help of MA model. So the today's temperature, tomorrow's temperature, again we'll consider C, which is a constant mean temperature, plus theta into epsilon 1. Now we were giving weightage to this error term of the first day, which is a difference of actual minus predicted. So C plus theta into epsilon 1 plus epsilon 2. Third day, C plus theta into epsilon 2, which is this, plus epsilon 3. Fourth day, C plus theta into epsilon 3 plus epsilon 4. Fifth day, C plus theta into epsilon 4 plus epsilon 5. Sixth, C plus theta into epsilon 5 plus epsilon 6. A small correction here. The correction is done. The generalization of the moving average model. The simplest moving average model is that of the order 2 or the MA2 model, which has the form yt is equal to ut plus theta 1 ut minus 1. That is the error at time period t minus 1 plus theta 2 ut minus 2. That is the error at time period 2, that is lag 2. Thus, the implication behind the MA2 model is that the yt depends on the value of the intermediate past errors, which is known at time t. Similarly, the MAQ model will be a moving average model of order Q, and will have a Q like terms as in the following. So this is a generalized model, and the last term is Q. ARMA model. They are the combination of autoregressive and moving average term. After presenting the ARP and the MAQ processes, it should be clear to the reader that we can have the combinations of two processes to give a new series of the models called ARMA PQ model. The general form of the ARMA model is an ARMA PQ, which is given by this. So these are the terms for AR and these are the terms for MA. Before we understand ARIMA, that is auto-regressive integrated moving average, it is necessary that we understand the concept of stationarity. Covariance stationarity of Y implies that over time, Y has constant mean, constant variance. Covariance between different observations do not depend upon time t, and it depends upon only the distance or lag between them. So let's understand this concept. In the first plot, uh, the dark blue line is a constant mean. The dotted blue line is a constant variance. Just see the distance between the dotted line, the dotted blue lines. It is constant over the time period. Moreover, constant covariance. See the distance between the red lines. It is also equidistance, and therefore constant mean, constant variance, and constant covariance. So this is the example of stationary time series. The second one, constant mean, the green line. It's constant. Constant variance, the dotted green lines. The distance is constant. Non-constant covariance, the distance between the red lines. It is now not equal, and therefore the covariance is not constant. The third example, time series with non-constant mean. See, the mean is changing. Variance is constant, the distance between the green dotted lines. Constant covariance, distance between the red lines. The last example, time series with constant mean, non-constant variance. The distance between the green dotted line is changing, and therefore it's a non-constant variance. Constant covariance. The distance between the red line is constant, and therefore it is a constant covariance. So the first is an example of a stationary time series. Second, third, and fourth are the example of non-stationary time series. With the help of some transformations like log and difference, we will convert the non-stationary time series into stationary so that we can apply the ARIMA models. Stationarity of the time series can be achieved by log transformation of the data or by first differencing. Both the methods have an advantages and disadvantages. The choice between them depends on the characteristics of the specific time series data you are working with. Let's see the advantages and disadvantages of the log transformation of the series. The first is variance stabilization. Stabilizes the variance, especially for exponentially increasing or decreasing trends. Disadvantage assumes a multiplicative rather than the additive relationship. Percentage change. Interpretable in terms of percentage changes. This is an advantage. Disadvantage. Not suitable for the data with zero or negative values. Additivity conversion. Converts multiplicative relationship to additive, make it easier to the model. Disadvantage. Does not remove linear trends or seasonality directly. Ease of interpretation. Log transform values often have a more interpretable scale. Disadvantage can introduce bias if the underlying relationship is not truly multiplicative. The advantages and disadvantages of first difference, if we take the first difference of the series, effectively removes both linear trends and seasonality. Disadvantage, sensitive to the choice of differencing order. Advantage, suitable for data with zero or negative values. Disadvantage, may introduce new patterns or structures in the difference series. Advantage, simple and easy to implement. Higher order differencing may lead to loss of valuable information. That is, if we take the second difference and third difference, so the data gets reduced. Stationarity induction aims to make the series stationarity, facilitating the application of time series model. Advantage. Disadvantage does not address non-stationarity due to changing variance. ARIMA modeling. ARIMA combines both AR and MA components, and it also introduces the differencing. Differencing involves subtracting the current observations from the previous one to make the series more stationary. So in the context of temperature prediction, you might work with the changes in temperature rather than the absolute values. Differencing helps to stabilize the mean and variance of the time series, making it easier to model and forecast using the ARIMA. The appropriate order of differencing is determined by observing the autocorrelation and partial autocorrelation plots of the difference series. Example, if the temperature data has a trend, ARIMA would first calculate the difference between each day's temperature and the previous day's temperature to remove this trend. ARIMA models can only be made on time series YT that are stationary. This means that mean, variance, and covariance of the series are constant over the time. However, most economic and financial time series show trends over time, and so the mean of YT during one year will be different from its mean in another year. Thus, the mean of the most economic and financial time series is not constant over time, which means that series are non-stationary. In order to avoid this problem and in order to induce stationarity, we need to detrend the raw data through a process called the differencing. The first differences of the series YT are given by the equation delta YT is equal to YT minus 1. The second differences can be taken as delta YT is equal to delta square YT is equal to delta YT minus 1. We go for the second differencing if we don't achieve the stationarity in the first difference. Let's see what actually we do on the raw data. This was the today's temperature. First difference 78 minus 70, 80 minus 70, 78 minus 75, which is 3, 80 minus 78, 2, 77 minus 80 minus 3, 82 minus 77, 5, 79 minus 82 minus 3. Now we will take the difference of this 2 minus 3, minus 3 minus 2, 5 minus 3, minus 3 minus 5. So this is the second difference. So now this difference series will become our dependent variable. So this will be known as integrated 1 and this will be known as integrated 2. So this is I1 and this is I2. So now what will be our ARIMA model? This is the actual data, first difference, which will become now our dependent variable. And tomorrow's temperature will be predicted with the help of AR and MA, both the terms. So C plus phi into 78, which is this one, plus theta into epsilon 1, this one. Then phi into 80 plus theta into epsilon 2, phi into 77 plus theta into epsilon 3, this one, phi into 82 plus theta into epsilon 4, phi into 79 plus theta into epsilon 5. So the ARMA PDQ, P stands for autoregressive, D is the difference that is integrated of which order? MA, Q is for MA. So if the series becomes stationary after second differences, then it is integrated of order 2 and denoted by I2. In general, if we difference a series D times in order to induce stationarity, the series is called the integrated of order D and is denoted by ID. Thus, the general ARIMA model is called the ARIMA P, D, Q, with P being the number of legs of the dependent variable, D being the number of differences required to take in order to make the series stationary, and Q being the number of leg terms of the error term. So the autoregressive component is AR is equal to YT is equal to phi into YT minus 1 plus epsilon T. Integrated is we take the first difference of the series and the moving average is YT is equal to theta into epsilon T minus 1 plus the epsilon T. The four stages of Box and Jenkins methodology in ARIMA modeling are identification, estimation, diagnostic checking, and forecasting. Let's see the flowchart. Plot the data, identify unusual observations, understand the pattern. If necessary, use the Box-Cox transformation to stabilize the variance. We can select the model manually or there is an automated algorithm also available for it. Select the model manually. Step 3. If necessary, difference the data until it appears stationary. Use a unit root test if you are unsure. Fourth, plot the ACF and PACF of the difference data and try to determine the possible candidate models. Fifth, try your chosen model and use the Akaike information criterion to search for a better model. The same thing you can do with the help of Auto.ARIMA. Next, check the residuals from your chosen model by plotting the ACF of the residuals and doing the portmanteau test of the residuals. Do the residuals look like a white noise? Yes, calculate the forecast. Now let's see how we can do this in R. The first thing which I have to do is import the dataset from Excel. The name of the dataset is beer consumption. Open, import. So this dataset consists of time, temperature, beer, that is the price of the beer, and the income. Now to run any analysis in R, it is necessary that we create the scripts. So click on plus, activate R scripts and start writing the script. The first command which we will do is attach beer consumption. That is, we are attaching the dataset into R. Run. Now to carry out the time series analysis, it is necessary that we install some packages. The name of the packages are T-series. So go in Tools, Install Packages, T-series, press here, Install. Make sure that your internet connection is on. After that, we'll have to activate this library. So let me take this hypothesis below this. Activate the library T-series. Plot the beer. And on right hand side, you've got the plots. Now we want to check the stationarity of this variable beer. Hypothesis: series is non-stationary or series has a unit root. This is our null hypothesis. Alternative hypothesis is series is stationary. Run the ADF test, which is the augmented Dickey-Fuller test. Run it and see the p-value. As the p-value is 0.6746, which is more than 5% level of significance, we fail to reject null hypothesis, which means that the series is non-stationary, or in other words, series has a unit root. So we will have to transform the series because the series is not stationary. So the first transformation which we can do is log transformation. So now we will do the log transformation of the series to make it stationary. So here is a transformation. Let me take it on the top. And so how we can create the new series? L beer is equal to log of the beer. 1. Plot L beer. So we got the new plot. Now we will have to check the stationarity of this new series. Hypothesis: series is non-stationary or series has a unit root. Alternative: series is stationary. Run. And again see the p-value 0.6431. This is also more than 5% level of significance. So as the p-value is 0.6431, which is more than 5% level of significance, we fail to reject null hypothesis, which means that the series is non-stationary, or in other words, series has a unit root. So we cannot use the log series. We will now carry out the first difference of the series. So as the log of the series is non-stationary, we will take the first difference of the series. How we can do it? Again, I will copy this here, and d beer is equal to difference of the beer. That is the first difference it will create. Hypothesis: series is non-stationary or series has a unit root, which is null. Alternative: series is stationary. Again, we will carry out the augmented Dickey-Fuller test. See the p-value. So as the p-value is less than 0.05, see this p-value is less than 0.05, we reject null hypothesis, which means that series is stationary, or in other words, series does not have the unit root. Now we will have to identify the pattern based on ACF and PACF. What are this ACF and PACF? Let's understand. So on the basis of correlation. We will plot the correlogram. So correlogram is plotted based on ACF and PACF. So it is a correlation between YT and its past lag YT minus 1. So autocorrelation function refers to the degree of correlation of the same variables between two successive time intervals. Partial autocorrelation function refers to the correlation between YT and YT minus 2 after removing the intermediate effect, that is YT minus 1. So that is a partial autocorrelation function. Now based on these two plots, we'll be able to identify that it is an AR model or a MA model. So if it is an AR term, ACF, if your model is having AR terms, ACF will be geometric, PACF will be significant till P lags, whereas MA, Q significant lags in ACF, PACF will be geometric, and if it is ARMA, it means that if your series consists of both AR and MA terms, ACF and PACF both will be geometric. Now let's see how we can do this in R. In my previous video, I've already discussed about the autoregressive model, moving average model. Please kindly refer to this. So let's run ACF 1. It's geometric. Run PACF. So it is significant till fourth lag. So what can be our interpretation? Let's see. PACF, P significant lags, and ACF is geometric. It means that the model should have the AR terms. Let's see. The interpretation is, as ACF is geometric and PACF is significant till fourth lag, so it is a AR process. Now we'll use the automatic ARIMA. For this, we'll require the library forecast. So we'll go in Tools, Install Packages, Forecast, install it, install, activate its library so that you can use all the functions of forecast, run, auto.arima. So it has identified that it is ARIMA 300 process. So AR3, there are three terms of AR. The alternative command for this is arima.final auto.arima dbr. That is a different series. Approximation is false. Press statistics true. Information criterion AIC. Test is KPSS. Run. So it also gives me the same thing 300. Now we will create the new series arima.final arima dbr order. So the series which is optimized is 300. So we will create that series based on this order C300. Run arima.final plot arima.final, and I will get the inverse AR roots of this. Now see this black points. If they are inside the circle, this means that the estimates based on AR model are stable. It is necessary that this black point should be lying within the radius of this circle. So the interpretation is, if all the black points lie within the circle, then estimates of the AR model are stable. One more thing, the ARIMA function will never return a model with inverse roots outside the unit circle. The auto.arima function is even stricter and will not select a model with roots close to the unit circle either. Okay. Now we will have to check the residuals of this model. What is our null hypothesis? Residuals are independently identically distributed, IID. So resid is equal to residuals arima.final, which is a diagnostic check for serial correlation. So we have created the residuals, or rather we have stored the residuals, and now we will run the junk box test. Box.test residual is equal to lag is equal to 10, type lungbox test, run, and we got the p value. So what is our interpretation? As the p-value is 0.2968, which is more than 0.05, so we fail to reject null hypothesis and conclude that the residual series is independently identically distributed. So this is quite good. Now we'll do the forecasting based on this generated series. So FDB here is equal to forecast arima.final, which is created above this one. And the time period for which we want to do the forecasting is 10 periods ahead. So H is equal to 10 FDB here. This is the forecasting. This is the forecasting. That is the low price of the beer and the high price, low and high at 80% confidence interval, low and high at 95% confidence interval. And we can also have the plot of this forecasted series run. So just see, this is the forecasting which we are having. Now, what is the model which we have created? So here is the model. This is our model. It consists of AR terms. So it's according to the correliogram, it is correct. There also the ACF and PSCF was displaying that it is having a AR terms. Now let's write the interpretation of this. Here is our model. dyt is equal to phi1 yt minus 1 plus phi2 yt minus 2 plus phi3 y3 minus 3 plus ut. So the db here is equal to minus 1.013 into yt minus 1 plus, let's introduce the minus sign only, that will be better. I will remove this plus sign, and here also I will remove this plus sign. So this is minus only, and here also minus. From where do I get this figure? 1.01 yt minus 1, 1.01 yt minus 2, minus 0.95 yt minus 3. So what will be the interpretation? A 1 unit increase in the value at time t minus 1 is associated with a decrease of approximately 1.0135 units in the current value at time t, assuming all other variables are held constant. Similarly to AR1, but for lag at time t is equal to a 1 unit increase in the value at time t minus 2 is associated with a decrease of approximately 1.0115 units in the current value at time t. Similarly, interpretation for lag at time 3. A 1 unit increase in the value at time t minus 3 is associated with a decrease of approximately 0.9574 units in the current value at time t. So this was all about ARIMA modeling in R. For more videos on econometrics using R, kindly subscribe to my channel. You can also refer my playlist in which I uploaded videos on data science, machine learning, and artificial intelligence. Please don't forget to like and share my videos. You can also join me on different social medias. Link given in the description box.